Hi, everyone. Thanks for coming. It's great to see everyone. I can see that keywords for high seminar attendance include juggling. Very happy to introduce Allen Knutson from Cornell University. He works on algebraic geometry and combinatorics, generally in research, but also does juggling. In fact, held the world record for two-person juggling with 12 balls for a number of years. He says it's gone up to 17 now. Yeah, this will hopefully be a livelier talk than some. So.
Thanks for having me. So I'm going to start with some not obviously juggling stuff and discover some juggling in it. So let's consider k by n matrices. And I'm going to be thinking about them like up to row operations. So we do this all the time. You know, in the very first week of a linear algebra class, you say, I'm writing down a system of k equations and n unknowns. I don't really care what the equations are. And that's about, but only what conditions they impose. So you put things in reduced to echelon form. That's what I'm going to be thinking about. But for right now, even though I'm interested in doing this up to row operations, I'm going to write it down as a list of n column vectors. All right, I want to give you a map from matrices to some other set. So a matrix will go in and some mathematical object will come out. But before I do that, let me extend my list of n vectors to an infinite periodic list. So I'm going to define Vn plus 1 will be defined as V naught, Vn plus 2, V1. Vn plus 2 will be V2, and likewise coming back, this will be Vn, and so on. So I've got now this infinite list of, of vectors, and the output, when this infinite list goes in, the output will be a function from z to z, and it should take I to the minimum j more than I, such that vector I is in the span of those later vectors. Okay? So that's our rule, that at each I, we compute this minimum. And so let's do an example. It'll almost look in reduced echelon form to begin with. It'll be a 4 by 6 example. Okay, so here's an example. So I'm going to be defining this function. This is at V1 up to V6. And maybe I'll just draw this, and it repeats. And maybe I'll just draw my function f with some arrows on here. So I take this column and I say, this column, when is it in the span of the later columns? And it's not in the span of this or this or this or this. In fact, it's not going to be in the span of any of these until we get back to itself. It'll be in the span of itself. All right, so we find out f of 1 is equal to 7. And similarly, this column is independent of all the other columns. Well, we'll start with this example, and we'll do many others. So this column is also independent of all the others, but it's not independent of itself. This column is dependent on the very next column. So we just get that. And we're going to see that sort of thing happening here as well. This column is going to be in the span of, I'm just going to wrap around here, not this or that or that or that, but this guy back there. So I'm not going to draw this arrow going back. Instead, it's going to go 5 steps forward. So if I wrote down, instead of these arrows, if I wrote down f of I minus I, then I'd be getting 6, 6, 1, 5, 1, 5. Okay? So that's what's coming out, this function. So you can ask, I mean, I had the continuous family, a whole vector space worth of inputs, and I'm only getting a discrete set of outputs. So you really want to know what f's can actually arise here. What are some conditions you know about this f? So really stupid condition is it's at least I, because I said that right here. okay? But also, it is at most I plus n. And that's because every vector is in the span of itself. So that's you don't have to wait forever, and you will in fact find that vector. Maybe in fact I'm going to write this instead as f of I minus I is between 0 and n. Okay. So next thing is to observe that if I start n steps later because of the periodicity, I'm going to end n steps later. So this guy, is periodic with period n. Okay? So already there's finitely many f's. So if I tell you what f is between 1 and n, and I tell you that what these numbers are, each number there's only n plus 1 choices, and I make those choices, and then you know what it's going to be for beyond that window from 1 to n by the periodicity. Okay, so that's still not specific enough. There's still more good things these f's do that are just automatic from them arising by this construction. So one of them is really interesting, is that this guy f should be 1 to 1. And so why is that? So if I had some vector that was landing sometime in the future, and some other vector that was landing sometime in the future, okay? So I've got I and j, and they're both going to k. What would that say? It'd say this guy you can write as a combination of these, and this guy you can also write as a combination, but only of those. And each time, that combination really should use k. If you can put coefficient 0 in front of vk, then you wouldn't be using it, and you'd be getting your min wrong, right? So each time I'm writing this guy I as a combination, and I use some of these, and I definitely use that. J definitely uses that. Take those two equations and cancel one off the other, and you can get rid of the k dependence. And now you've managed to write I not using k, and you had the wrong minimum. So that's the linear algebra proof of this one-to-oneness. So that one-to-oneness and this periodicity, this is enough finiteness going on here to find out that this is actually one-to-one and onto. So we're thinking about permutations. And when you have the periodicity and this thing being a permutation, those are called affine permutations. But we've got more than just the periodicity and the bijectiveness. So if you consider if you said I'm just interested in being periodic, f of I minus I is periodic, and my permutation is it's an actual permutation of the integers, there's a group of those, right? That's a nice subgroup of permutations of z. This thing is not going to be a group because if you took an f that's like that and you inverted it, if you took an f that did this and you invert it, then instead of these arrows all going to the right, they're all going to go to the left, and we'd have f of I negative. So we're not getting a group. We're just getting some interesting finite subset of the group of affine permutations. Okay, there's one more condition that f needs satisfy, and I'm going to state that as a theorem, that there's one more. So when you think about k by n matrices, and particularly you think about them up to row operations, it's a little weird to allow even like the 0 matrix to be in there at the same time as a generic matrix, because what's really nice is to consider the row span of those of that matrix, and that will typically be some k-dimensional subspace, assuming k is less than n, which I'd like to assume. So usually I'm going to be getting a k-dimensional subspace, and every now and then it'll be a dimension lower than k, and those are just kind of confusing. So let's assume that we're dealing with rank k matrices. And then what turns out to be here is that the average of this will come out to be k. So let's do an example. What if this example is an example. The average of these numbers is 4, okay? And this is a rank 4 matrix. So generically what's going on, generically, if I just write down random numbers here, then what's going to happen? So the generic matrix will map to f of I is equal to I plus k for all I. That a column will not be in the span of the next k minus 1 columns, but the k columns after it will be a basis, and so it will be in the span of the next k columns. And that'll just be true at every step. So that's the usual case. And the least generic is things where you have like maybe the identity matrix in some columns, and you've got 0 everywhere else. And in these least generic, and there's n choose k, many least generic possibilities where k of your columns are a basis to get you the rank k, and everything else is 0. In those cases, what's happening with these 0 columns? So these 0 columns, I'm trying to write my column in the span of later columns. I don't need any of these. I could take j equal to I, this to be the empty set, and I would write my 0 column as being in the span of the empty set. So in those cases, I'm getting zeros for my f of I minus I. And in the other ones, I've got a column that's just in the span of itself, and I'm getting n's. So these are the extreme cases where I've got just n's and zeros, and this is the generic case where I've got all k's. But in both extremes, you're seeing this average happening. All right, so I'm going to state a theorem that if you consider all of these conditions coming from rank k matrices, that this map is onto. So really, these are the conditions on such a function. I came up with various extra things that these functions are supposed to do, and that's the complete list. All right, so how do you interpret? So I read about these first in this paper by Sasha Postnikov from 2000. Well, it was never published, so I think it went onto the archive around 2004, and it's called Networks and Parameterization, and it's a couple other words. But the paper is still pretty incomplete. Like section 17, there's the title, and then there's section 18, and there's nothing in there. And at one point, David Spire told me, so I've written a paper that I believe is supposed to be section 17, at least based on the title of that section. It's been a very influential paper. I think it was definitely helped in getting him his job at MIT. And so I don't expect it to be published, though. But in that paper, he does a lot of thinking about decomposing the space of k by n matrices, or really, remember, this was up to the left action of invertible matrices doing these row operations. So you could say up to row operations. And so it's getting you a decomposition, not just of the space of matrices, but of the Grasmannian, of k-planes and n space. So if I consider that set, so what would I do? I take a k-plane in n space, I'd pick a basis for it. I don't care which basis it is because I'm going to lose that as I start just comparing spans of column vectors. And it's getting me this decomposition of the Grasmannian. Anyway, I read this paper, and at some point I said, oh, they're juggling patterns. Why didn't he say so? So he defines this. He doesn't talk about these. He talks about various other things like Plabic diagrams and decorated permutations and law diagrams. He has about 6 different ways of defining what I like to think of as this set. And he never says should. He never says, if you want to understand this thing, you should think about this version of the definition. So I'm going to tell you you should think about this one and say now what it's got to do with juggling. So what a juggler does with a function like this, the interpretation is that a ball thrown at time I is caught at time f of I minus a half. So then thrown again at time f of I. And so let's do some examples. So what jugglers do is they don't actually say like f of I equals I plus k. Instead, jugglers will give this list, like this thing here. They'll tell you what f of I minus I is equal to for I running over one period, and say that's a juggling pattern or a site swap. So let me write down a bunch of examples of these. So I'm going to, for the juggling purposes, I'm going to impose these conditions, and we'll talk about them in a little bit. I don't, so this condition is less important for jugglers.
Sorry, it should be less than n or equal, less than or equal n.
It can be n, as you saw here.
Okay, fi minus I never goes to 0.
It can also be 0, but not in that example.
Okay.
It was 0 in these examples. Yep, both extremes occur. So 0 is when j is equal to I and there's nothing here. And that can happen if you have the 0 vector, if and only if. So you'll get a 0 if you've got a 0 column, and you'll get an n if your column is independent of the other columns. All right, so I'm going to write down some examples. 3, 4, 3, 1, 4, 4, 1, 4, 4, 1, 3. I guess at some point I should do 6, 6, 1, 5, 1, 5. Okay, let's start with those. So 3 means, okay, so this thing, this ball thrown at time I, let me make the assumption that I'm alternating hands, okay? So this is just an artistic thing. You could say that really mathematically what we're talking about here is one-handed juggling. And I'm just going to replace one-handed juggling with alternating hands. And the mathematics isn't going to care. So what's going on with 3 then is whenever I do a throw, there's going to be 2 other throws that happen in between, and it'll land, it'll be the third one to be thrown again. And that's what's going on in this pattern with these 3 different balls. So while one of these is in the air, like that guy, I do these 2 other throws, and it gets thrown again. So every throw here is the same. Some are from my left, some are to my right, but that's because I'm alternating hands. 3 is an odd number, and that has to do with each of these throws crossing. So because I throw it from my left hand, the next time it's going to be thrown from my right hand. All right, so 4 is like that, except again, I'm alternating hands, I'm doing an even number throw. So while I do one of these throws, 3 other throws are going to happen, and it's then going to come down to be thrown 4 steps later, which means in the same hand. So all of these throws look like this. They don't cross from one hand to the other. And if you're wondering, is that really juggling? The answer is yes, of course it's really juggling. So this is just one way to do 4 according to the, what's the rule I want? The rule is while something's in the air, then I do 3 other throws. And there's no particular reason that I would do them, circling around this way, or there's plenty of choices here. And that was true back with 3 as well, that instead of doing 3 like this, I could do 3 where all the throws are from the outside to the inside, or maybe I could mix and match. Right hand's going outside throws, left hand inside throws. There's plenty of other things, there's plenty of other things you could do that just while one throw is in the air, you do the other 2 throws. So numerically, this is just the pattern 3, 3, 3, 3, 3. Which means maybe it's kind of disappointing that the site swap, or writing down here this list of numbers, that it's keeping track of so little of the juggling pattern. And if you want more, well, you can start notating it, right? And then you start getting into like, dance notation sort of things. It's and less into a mathematical theory.
Is the fact that you said that less than or equal to n less important because you can just turn 3 into 3, 3, 3?
I just want to say that jugglers know what to do with any juggling pattern that's specified that satisfies all of these rules and doesn't satisfy that. And for the juggling point of view, this is just not a natural thing to impose. So in particular, this is disallowed by that, right? It's a length 1, but I've got a height of 3 in it. And yeah, could I interpret it as 3, 3, 3? Yes. If I were telling somebody, if I say to somebody I'm interested in this pattern 5, 6, 1, they're going to think it's weird if I say I'm interested in the pattern 5, 6, 1, 5, 6, 1, because for some reason I felt like extending it to be length 6. So the jugglers they just don't care about this. Yeah.
I think I missed it, but what's 3, 1 mean?
I haven't gotten there yet. I'm going down in the.
Permutations of 3 and permutations of 4.
So what each of these numbers, what these lists are in each case is this list fi minus I running over 1 period. So 3, 1 is the one I'm going to do next right now. So it's length 2. It's an even length pattern, and as such, it's going to be asymmetric. I'm going to go 3, 1, 3, 1, 3, 1. And so 1s are really easy. Okay, here's the 1-ball pattern. And while it's in the air, I do 0 other things. All right? So I'm going to be doing that with my left hand, but my right hand is going to be doing these. And so together it's this, right? I think you've seen this before. So this is the pattern 3, 1. And it's alternating 3, 1, 3, 1. All right, so 4, 4, 1 is more interesting. And actually, maybe I'll draw it this way. So imagine I've got a camera in the ceiling, and it's looking down. I'm juggling glowing balls, and the camera is looking at the tracks of the balls. So it's only seeing that they go left to right between my hands. It's not seeing the up, down. And what that camera would see would be something like this. Right, so this direction is time. So here's my left hand, here's my right hand, and it's seeing the balls go from my left hand to my right hand and back. And so I'm going to draw on the board first a trick I'll do in the middle of a pattern, and then you'll see it in life. So from this right hand, I'm going to throw back to the right hand. I don't want to throw to then, because there's a ball landing then and I'll get a collision. So that would look like if so like things like this, those are really hard to pull off. I was lucky this time, all right? So I'm not going to be doing juggling patterns like that. So I'm going to do this not to land then, but here where there's a hole. This guy, likewise, I'm going to throw it all the way out there. And this one I'm going to throw really fast straight across. So this thing is higher slope than those were, which means it's covering more space in less time. It's faster. But then I'm just going to go back to these ordinary throws. So what the numbers are here is I'm going 3, 3. Let's get this a little bit over there. Okay, 3, 3, 3, 3, 4, 4, 1, 3, 3, 3, 3. And what I was writing down there is, again, how many other things happen before that ball gets thrown again, plus 1. So you know what 4s look like, you know what 1s look like. And so in the middle of 3, at some point I'm going to throw this red ball as a 4, and it's going to start off the 4, 4, 1. So not that time. Nope. All right, this time. 4, oops, I thought so. All right, next time. 4, 4, 1, okay? So again, 4, 4, 1, and then back into 3. 4, 4, 1, 4, 4, 1, 4, 4, 1. All right, so now I'm just doing 4, 4, 1. So I'm getting this pattern that looks kind of symmetric over, if you look over a long enough period, because it's an odd length pattern. So sometimes it starts right-handed, sometimes it starts left-handed. And if you think about what any single ball is doing in this case, any single ball is going, so in this 4, 4, 1, it's being thrown as a 4, and then going 1, 2, 3, 4 steps over. So So I'm just going to write it on one period rather than repeating this thing. This guy is going to come down 1, 2, 3, 4 steps later. And this guy is going to come down 1 step later. So any single ball does, it goes hop, hop, cross, cross, hop, cross. All right, 4, 4, 1, 3 is actually maybe simpler to think about. It's going to have a ball that goes from the right hand to the right hand, left hand to left hand, and then right hand to right hand. And then I'm going to hand one right across, and then it'll come down 3 steps later back over there. All right, so what that looks like, I'm going to start with this as the 3. So there's going to be a 3, and then 4, 4, 1, 3, 4, 4, 1, 3, 4, 4, 1, 3. Oops. So 3. So there's the balls that only do 4s. I didn't stand in front of it. Good. There's the balls that only do 4s, and you see them hopping up and down on the sides. And then there's the ball in the middle, the red one, that's going alternating, doing 3s from my right hand, 1s from my left hand. Okay. So I introduced to the jugglers this concept of an orbit in a permutation. So this permutation of integers mod 4, this permutation has 3 orbits. These 2 fixed points and this orbit. And different balls doing in different orbits or doing different things. So 661515 is like that, except let's check it out orbit-wise. There's going to be these 6s, and then a 1, and then a 5, and then a 1, and then a 5. So it's still going to have this frame around the outside of these 2 balls that are just hopping on the sides, but now it's going to have 2 balls going around the middle doing 1s, 5s. I guess before I do that pattern, maybe I'm going to do this one, 5-1. So 5-1 is like 3-1, except while one ball is in the air, one of these high throws, I'm supposed to be doing 1, 2, 3, 4 other things. And so it's actually a 3-ball pattern. And this pattern is much harder than this pattern. You see I'm doing them approximately the same speed, and yet I have to be able to handle throws like that. And of course, then there's 7-1, and there's a bunch coming that way. But what's going on here, each of these balls thinks it's in this pattern, right? But the ones on the outside think that they're in a 6 pattern. All right, so there's the 2 in the middle, and the 2 around the outside. All right, good enough. So, how about 4-2, 4-2-3, 4-0? So maybe I should even do 2 as a pattern. So what a 2 looks like, it's supposed to be some little throw that goes from the hand back to itself because it's a low number. And while it's in the air, you get to do something with the other hand, and then it should be the next one. And there we go. There's 2s. So remember there was like this artistic interpretation before of what do you actually want to do when somebody gives you this list of numbers? Do you really want to throw them like this, or do you want to do something else? So 2s frequently are just not thrown, okay? So I might say this is 2, 2, 2, 2, 2. So this 4-2, I'm going to be alternating doing 4s in one hand and 2s in the other. And people do lots of stuff with this. So there's there's a string connecting them. There's eating the apple trick. When you see people do something where they need to not throw a ball at some time, then it's probably a 2. So 4-2-3, let's see the orbits on there. 4 is coming down 1, 2, 3, 4 steps later. 2 is coming back there. 3 to itself. So there's going to be, let's see. Yeah, it's this one. So there's going to be this ball that's doing 3s, and the other balls are hopping and then just sitting. Okay. So how about 4-0? So something I haven't emphasized yet is how many balls there are in a pattern. And you might have noticed, like, when we did 3, there were 3 balls. When we did 4s, there were 4 balls. And obviously, if I'm just going to do k all the time, then that sounds like a k-ball pattern. That while I do it, I can throw the other k-1 balls. So like here's a whoops. not there, here. Here's all 5s. So while one of those is in the air, I'm doing 4 other things. And that's, yeah, and I did, so you saw this now with 3 and 4 and 5 and 2. And I want to do the same thing with zeros. I'm going to interpret a 0 as an empty hand. So here's the pattern 0, 0, 0, 0. But 4, 0 is this pattern, okay? I'm alternating 4s in one hand and 0s in the other hand, not to be confused with 4, 2, which is a pattern with one more ball, okay? All right, so let's prove some more theorems. Now we have some examples to work off of. So theorem, and I do not know, I should say something about the history here. So this stuff is all from, not all of it, but this numbering system for juggling patterns was invented by the jugglers in like 84, 85, and by these 3 groups pretty independently. So one group was at Caltech, and one of the jugglers there was so impressed by, was not a mathematician, was so impressed by the statement that you can generate any permutation as a product of transpositions that he named the theory after that, and they're called site swaps. So for him, an elementary site swap is where you swap two positions. I'll deal with them in a second in the theorem. There's another group in Cambridge who invented what was called Cambridge notation. That name hasn't stuck around as much as site swaps. And then there was this, this really curious guy in Santa Cruz who invented quantum juggling, a name that really has not stuck nearly as much as site swap has. So I got into this in '88. The stuff relating it to matrices and so on, that's more like 2009. So I was thinking about this for quite a while before connecting it to my day job. All right, so here's a theorem, and I think this theorem is one of the first things I learned in the subject, so I think this is already mid-'80s stuff, is that the average of the site swap, and so remember this is not the f itself, but the f of I minus I, is equal to the number of balls. So for example, in 4-0 we had 2 balls, and in 4-2 we had 3 balls. Okay, so here's those averages. And so the proof is, I'm going to prove it really with an example so you see just what goes into it. So let's start with 5, 1, 4, 1, 4. And the average is 3. And if I draw a picture like this, well, I don't know, I'll have this 5 and this 1 and this 4 and this 1 and this 4. And I'm going to look through my site swap for a place where there's a descent, where I have an earlier throw that's going to come down after a later throw. And so like, instead of like 4-4, where I throw them in a certain order and they land in that same order, so like 5-3, where I throw them, but the one that's being thrown second is landing first. So I've got that here with this 5-1. And what you can do is this little bit of surgery on this picture to get them to swap, so that the ball that was thrown at time 5, instead I'm going to hold it one step and throw it at time 4. To land 4 steps later. And this one, instead of being thrown then, I'm going to throw it from earlier, but still to land at the same time. Okay? And then everything else stays the same. And let's keep doing this. So I'll look for a descent here, 2, 4. This will turn into a 2 and a 3. And then another descent here, 2, 3, 3, 3, 4. And in general, what's happening is I'm replacing A, B with B plus 1, A minus 1. And as such, the total is staying the same. And as such, the average is staying the same. So as I'm smushing my pattern to be more and more even and closer to be the all K's pattern, I'm not changing the average, and I'm also not changing the number of balls. I'm just changing the order that the balls are landing. Okay? But now I'm stuck. Am I stuck? Why am I not stuck? Because it's cyclic. I can think about going one step further and getting to all threes. And so, you need to prove some inductive thing that says you will always make it down. Okay, but there's a scary thing to worry about this. What if I had something like 5, 4, and the 5 turns into 4, and the 4 turns into 5? What am I supposed to do in this case? So I wanted to get down to all the numbers being equal and using this trick. But what's going on with this syndrome? Yeah, that wasn't actually valid, right? If I had a 5 and a 4, see, they're landing at the same time, and that's not what you actually have. So when I said, these things were when I was looking for A more than B, but in fact A is going to be more than B plus 1. And I'm not going to run into this as a sticking point. So then you get down to all the numbers being equal, and the jugglers at that point say, obviously, the number of balls is that number. Let's see.
Can I ask a pattern question?
Yeah.
Can you have a 4-ball pattern that you alternate hands?
I mean, that's
No, like the balls alternate hands. Sorry.
sure. So let's go with 5-3 as an initial one. How about 5-5-2, 5-5-5-1? What's the next in this sequence?
5-5-5 is 0.
Yeah. Okay, what's the next in this sequence?
5-5-5-5 minus 1.
Yeah, let's talk about that one in a bit. Okay, so I'm going to do some of these, and we'll think about them in order. So 5-3 is even length. I'm going to be always doing 5s from here and always doing 3s from there, and it looks like that. Or way it looks, right? I mean, I could do the 5s inside the 3s as well. I think it's prettier with it outside, but whatever. So there's such a pattern. Incidentally, you could ask, given 2 throws, how high is one relative to another? So if I want, so the height of an M throw versus the height of an N throw is you subtract 1 from each, and that's to accommodate for the time spent in the hand. That a ball, so when I'm juggling like all 5s, each of those 5s is in the air for 4 beats and in the hand for 1 beat. So that's the time ratio, and you got to square it to get the height ratio. So what's going on with 5s and 3s is the 5s should be 4 times as high as the 3s if I want the rhythm to be even. Oops. So that's reasonably even. Oh, and I should have dropped into 5-1 at that point. All right, so that's 5-3. So 5-5-2 is odd length, so it's symmetric, and it's just going to have 5s, and both hands are going to do 5s, and there's going to be the occasional 2. So it looks like this. So there's the 2s. Okay. 5-5-5-1 is some mix of 5. So my left hand is going to alternate sometimes 5s, sometimes 1s. And so it's going to look like this, except that half the time my left hand is going to be throwing high. All right. Now 5-5-5-5-0, that's exactly, I'm trying to do a 5-ball pattern, but 1 ball is missing. And just have an empty hand whenever that's going to come up. And so the way to not do that is this. This is the lazy way to do 4 balls out of 5, that whenever you can wait, you wait. And this is the excited way to do 4 balls out of 5. All right. Oops. Ah, man. Yeah. Now, 5, 5, 5, 5, 5 minus 1. All right, let's go back to this picture and get some idea of what that would look like. So maybe I'll do a smaller one. How about 2, 0, negative 1? So, all right, I guess I really just want to. So I'm going to do 2, 0, negative 1, 2, 0, negative 1, 2, 0, negative 1, 2, 0, negative 1. Okay, so the 2 is going to go there. The negative 1 is going to go back there. Shoot, this should have been 2, negative 1, 0. All right, let's try that again. 2, negative 1. Do I mean that? One sec. I don't think I mean either of those. I better have an average of an integer. So let's try that better. How about 4, negative 1, 0? Okay, so 4, negative 1, 0. What would the orbits look like? The 4 is going to come down 1, 2, 3, 4 steps later. The negative 1 is going to come down 1 step earlier, and the 0 to itself. Good. Okay. 4, negative 1, 0, 4, negative 1, 0, 4, negative 1, 0, 4, negative 1, 0. Okay, how many balls does this pattern have? 1. The average is 1. All right, so the 4 comes down then, which comes back to then, which comes down then, which comes back to then. Okay. Okay, what does one see watching this juggler? Like, if you, so remember this is time, right? So we got this space-time direction, okay? So if I just take a snapshot at some fixed time, I say, what do I see now? The answer is I see a ball, okay? What do I see later? Well, I see a ball. Okay, what do I see now? I see 3 balls.
One is a negative ball.
But 1 is an anti-ball. Yes, yes. What happened there was ball, anti-ball creation, okay? And so ball, anti-ball creation, and then it gets over to here, and it's gone. Over here we have the ball, anti-ball annihilation, okay? So this is why the jugglers are insistent on this condition, but not the other one. There's an excellent YouTube video from like, I don't know, 12 years ago that called Negative Site Swaps that demonstrates these. So this dude has these glowing red and blue balls, juggles them in the dark, and turns them on and off appropriately to demonstrate creation and annihilation. And does some pretty complicated patterns. Yeah, so mathematically the negative one's perfectly nice, and the physical interpretation is clear, and you can see it on YouTube if you want. All right. So we have a choice with the remaining time of how deep a mathematical subject I get into. So let's start with one easy statement, and then talk about some subtler stuff. So so theorem, and this is in this paper called Juggling, Drops, and Descents. From 1994 in the American Mathematical Monthly, and it's by this chair of the the AMS and by this chair of the AMS, or president, I guess, of the AMS, but also president of the International Jugglers Association, and these other fine people who were into those things, Joe Bueller and Colin Wright, is the number of patterns with length n and at most b balls is b plus 1 to the n. So that's a nice little theorem. And their proof is pretty terrible in that paper. It's really not very satisfying. I think a few different people figured out a better proof. One of them was definitely Bill Thurston. So Thurston's proof is that we're going to do a tarot reading with the following deck. So the deck is going to have B cards with repetition. So as many cards of the same kind as you like, but B cards where we connect these B dots to these B dots in the following way. One of the dots bounces off the ground and comes barely back up. And dots above it go straight across, and dots below it get promoted 1. Okay? So there's B like that, depending on which of these dots is the one to do the bounce. And again, everybody above, straight, everybody below, increased by 1. And there's going to be one more card, which is that nobody bounces. Okay? And to emphasize, this card is not the same as the one where the bottom guy bounces. We consider them different. So that there's B plus 1 cards, not B cards. Okay? And then we lay out n of these to side by side. And there's clearly B plus 1 to the n, many tarot readings to do like this. And then we read off a pattern. So I'm going to do an example. Let's have this guy bounce, and then that one bounce, and then nobody, and then the bottom one. Okay? So what happens here? I throw a ball, and it goes up into the air, and it comes back, and it's here so far, so that's 4 steps later, and then it lands. So this was a 5. This one I throw up into the air and it lands 2 steps later. This one, there's no throw at all. That's a 0. This one I throw it up and it comes to there and to there. And then it goes to there, so that's a 2. And the 5 kept going. This is no good. Yeah, that's right. So it came to here, it's in the second tier. That means there. That's what I did wrong. But then it goes around again to here, and then it finally comes down. So it's an 8, in fact.
And there's a ball going around all the time.
And there's this ball that's stuck on the ceiling, yes. And that's why we have this thing, the less than equal, to account for the fact that some balls are just stuck on the ceiling. Okay? So that's the good proof.
Don't you have problems with cycles? Like if you had the same, or do you take them up to?
Oh, depending on your definition of of a pattern. Do I count this as the same as 2, 0, 2, 8? I do not. Yeah. All right, I think I'm just going to, having rushed through that, but that's complete, I'm going to rush through some algebra geometric statements. So recall from the beginning that we had the Grasmannian of k-planes in n space, and we wrote it as this decomposition of these pieces, which were, and there was one for every bounded affine permutation, such that the average of f of I minus I was k. And then we get some stratum that I'm going to call pi sub f open. So f is running over these, and I get and so this is this was those K-planes inducing the affine permutation F, according to the rule at the beginning. Okay, so here's some theorems of me and Thomas Lamb and David Spire. We have a paper with juggling in the title. And this is from, I think, 2010. Are one, these guys are smooth and irreducible. And this is pretty close to something that's already in Sasha Postnikov's paper. So maybe I'll put him there as well. So not quite the same, but quite close. This decomposition is a stratification. So that's a technical thing about a decomposition that you like in order to get like good partial order theoretic properties. It says when you take one of these pieces and you take the closure, you get a union of other pieces. So let me give you a non-example of a decomposition. I'll give you a decomposition, but that isn't a stratification. I'm going to break up this trapezoid, this solid trapezoid. I'm going to break it up according to where you end up with if you flow downhill. So this guy's all by itself. Then all this stuff flows downhill to here. This stuff flows downhill to here. And most things flow downhill to here. And what I don't like is if you take the closure of this thing, you get just that point. So I've broken this thing into 4 pieces. A point, a clopin interval, and the rest. And the problem is that the closure of this clopin interval isn't a union of these pieces. So this is not a stratification. I'm telling you, oh good, this decomposition, the Grasmannian, isn't like that. It is a stratification. If you take one of these things and you take the closure, then it has all of these nice algebraic geometry adjectives. So I'll just say normal, Cohen-Macaulay, rational singularities, compatibly Frobenius split. All right, there's some adjectives. So the point is, there's a whole bunch of algebraic geometry to be done here, and we've done some of it. And there's lots more to be done. I'm not going to get into physics connections, but some of it is definitely related to scattering amplitude calculations in physics, as studied by Arkani Hamed and co-authors. So there is indeed a paper by Postnikov and Arkani Hamed and a few other mathematicians and physicists about the physical reasons to think about this stratification of the Grasmannian. All right, I think I will finish with a more combinatorial thing you could ask about the juggling pattern. So I'm going to give you this deeper level into the patterns where we're going to think about them as transitions between various states of a juggler. So imagine that I'm juggling 3, and I stop, and you listen, and you hear catch, 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 nothing, 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 nothing. Okay? I'm going to write down that as I had catch, 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 nothing, nothing, nothing. Okay? So that would be different if I were showering 3 balls, as this is called. These all have these water names. So this is the cascade, this is the shower, this is the fountain. Here's the fake shower. But anyway, the shower, if I stop just after making a left-hand throw, you hear catch, catch, nothing, catch. All right? And so that's what I'm going to call this state of the juggler. And I could keep saying nothing happens after that, but let's just stop there and say I'm in that state. And that would be different if I were doing this and I stopped after one of these throws. then there'd be catch, nothing, catch, right? So there you see that. And so that would be this state. So the difference is that this, I stopped here just as I was about to do a 5, right? So I had just done a left-hand throw and I'm about to do this 5. The 5 is taking the ball that's landing right now and saying, put it into the air to land 1, 2, 3, 4, 5 steps later at this spot. So imagine I chop off the beginning and I put that in position 5 and I get to here. Okay? Versus here, this is just after I did the 5. Next thing I'm going to do is the 1 in this pattern 5, 1, 5, 1 I was doing. So I'm going to take this thing I'm catching right now and chop it off and put it there. And I'll get XX-X, which is this. So there you see 5, 1 is that loop in this thing. So here, this one's kind of silly. This was the ground state where things are as close to being caught as possible. And here, I could take this guy and throw it to then, and this will just repeat. And there's the cascade. So what's good about this sort of picture of things is it lets you figure out transitions really nicely. So if I'm juggling the 3-ball cascade and I want to do the shower, I need to get from here to there, and it's sort of obvious how to do it now. Put this, not then, but then, and get to XX-X, doing a 4. And one of the ways I could get back is at this point I could take this ball and just hold on to it until it ends up in there, and that'd be a 2. So let's see that happen. So I want to do this 5 for my right hand because I'm right-handed. And so I'm going to be doing, just before that 5, I'm going to be doing a left-hand 4. So I'm doing 3s, and then there's a left-hand 4, and then I get to do 5, 1. Okay? And then there's a 2, and I'm back to doing 3s. Okay? 4, 5, 1, 5, 1. Oops. 4, 5, 1, 5, 1, 5, 1. And then 2, and back to doing 3s. Okay? Oh, that wasn't it. So I don't like 2s. They're boring. So if I don't do a 2, I can't do a 3. The next thing I could do is a 4. And I would get to X-XX. Okay? And from there, I could do a 1 and come back to here. So that's a different way to, so I'm be doing these 5s from my right hand. You see these high crossing 5s. And at some point I'm going to do a 4. And then I'll be back at doing 3. So I'll be going 5, 1, 5, 1, 5, 1, 4, 1, 3, 3, 3, 3, 3. Right? So 5, 1, 5, 1, 5, 1, 4, 1, 3, 3, 3. Okay? 4 to get back in. 4, 1. Right? Or I could go 4, 1, 4, 4, 1. You've seen this guy before. So there was the 4, 4, 1 from a long time ago. Or there was the 4, 4, 1, 3, 4, 4, 1, 3. That was the one that had this ball in the middle doing 1s and 3s. So there's plenty of things to do with this graph, mathematical things to pursue. Like, let's say we fix the number of balls. Well, then there's infinitely many states. But let's also fix maybe the highest throw. So then there's only n choose k many states for us to be in. And you could imagine randomly juggling in the sense that at every time you do a throw, you look at one of the n minus k times you could throw that ball to and pick them with equal probability. And, and you get this Markov chain on n choose k. And there's a paper called Juggling Probabilities by the 9-ball juggler Greg Warrington, in which he computes the stationary distribution of that Markov chain, and the numbers are some multiple of Stirling numbers of the second kind. So I've got a paper that takes this thing and flips all the arrows. And one thing you can do with that is consider n to infinity. So I changed the probabilities a little bit on it and get some pretty sweet answers, I think. And the paper's called Randomly Juggling Backwards. And there's variants of it people have done where so the jugglers think about variants of this where, for example, instead of just having one list of holds or catches or not catches, you've got 2, And that's the sort of thing you're going to want to study if you're doing synchronous patterns. And there's plenty of good synchronous patterns out there. I didn't talk about them yet because mathematically they're about functions not from z to z, but from z cross number of hands to z cross number of hands. But it fits into this picture well too. I guess one other thing that's fun with this picture is you can handle what are called multiplexes pretty nicely as well, where you've got sometimes multiple balls being thrown at the same time. So this doesn't show up in the matrix story so much, but the jugglers are interested in things like that. All right, I'll stop there.
Thank you. If there's any questions, please wait for the microphone.
How does this interact with dualizing in the Grasmannian?
Yeah, kind of badly, I think. So the problem is that the jugglers are, they're much more interested in K than they are in N, right? And, do I want to consider the pattern, say, do I want to consider the pattern 333 as the same as the pattern 333, 333, or something like that? And the jugglers are going to basically say yes, but then as you change N, that's going to change N minus K. And so I'm pretty shocked to have never thought about this exact question before. But I think it's because from a juggler point of view, N is just a weird thing to consider. So on the in terms of the stratification of the Grasmannian, there's no change. So the isomorphism of the Grasmannian with the dual Grasmannian will take this stratification to the stratification there. So.
I'll jump in with one then. So you had these patterns that kind of were smaller than n, and so it's sort of you repeat the pattern eventually. If I just repeat the pattern until it is longer than n, am I guaranteed then that this now fits the original definition of f in the matrix?
Yeah. So that was the ontoness question from the beginning. So which f's actually arise? And the answer is if your f is an affine permutation, so it's got the periodicity and it's invertible, right? And the values are always between 0, f of I minus I is between 0 and n, and the average is k for your particular k Grasmannian, then yes, there will be matrices that do that. And we can say more, like we know what the dimension is of this stratum. It's a pretty simple formula in terms of the sort of excitation number of the juggling pattern. But in particular, it's not empty, is kind of your question. Oh, to tie this to yesterday's lecture, one thing of immense interest is you take one of these guys, take the closure, and it's now defining a subvariety of the Grasmannian. What's the class of that subvariety? It's going to be some positive linear combination of Schubert classes. What are those coefficients? So that doesn't sound like a multiplication question, but it turns out to be exactly equivalent to the question of I'd like to multiply two classes on the flag manifold, one of which was pulled back from the Grasmannian. So it's called the Schubert times Schur problem. And there have been announcements, alas, on the archive of formulae for this that then have not held up. So it's still an open question and very important, is what are the classes of these things?
Other questions? All right, well, let's thank Allen again.